I'm Julio Belmonte, professor North Carolina State University. And today, and in this module 1.2, we're gonna go over a little bit of how the cellular POTS model works, how exactly we are simulating those cells. Then we'll work on play with contact energies, which is the very basic energy that you actually use for out simulation to have contact energy. The cells do adhere to one another, and we're going to use that to maybe explore some mesenchymal to epithelial to mesenchymal transition, which is something that we can actually play with by just changing the contact energies between the cells. Okay. I would like to ask if everybody's hearing me correct, right? Can you understand what I'm saying? Is there any problems with the audio? If
No, looks
everything's
good.
looks good, okay. The neighbor here just started cutting his grass, so there may be a little bit of noise, but hopefully that will be done, be over very soon. Okay, so again, if you have any questions, you need any help, please send a message through the chat or through the Slack channel, and let's get started. Okay, so the what we're doing today is going a little bit of cell modeling, a brief intro to CPM or Glaser-Granet-Hogweg modeling basics. Okay, just for you to enough for you to understand what is going on when you actually run simulation. I'll give a motivation of epithelial to mesenchymal transition or EMT, and then we're gonna do a step exercise with the very basic module function of CompuCell, which is the contact energies, right, which you can use to actually model the epithelial mesenchymal transition in a very, of course, simple way. But this is a very basic simulation or very basic mechanism that is very good that you understand exactly what's going on and how to model it, how to manipulate it to get the simulation to look like and the cells to behave exactly like you want it to be, and to close uh, match what the cells actually look like in the experiment or the in vivo situation that you want to reproduce. Okay, so what we are doing here in this with the CompuCell3D player, we are basically simulating cells. Okay, so here is a figure of a bunch of cells in an epithelium. In green is the nucleus, in red is the membrane, and you can tell that the cells are closely packed. Okay, and you can actually see the double membrane here, membrane of this cell and the membrane of that cell. I hope you can see my mouse, so I'll be using a lot to point up things. And then, okay, if you want to model those cells, there's basically four ways to do it. Well, there are many ways to model those cells. James did cover some of them in the previous lecture. So, so one way to model the cells in a computer is, okay, maybe I can have a grid, a square grid like this, and I can fill up the grids wherever I see a cell in that point in space. So here I overlay a square grid on top of my image, and whenever I see a nucleus, I color in green and say that this is a cell. So this is called the cellular automata model, and was one of the very first ways to actually model cells and living things. But of course, the only thing you can do is can actually move the cell over space by advancing one square letters. Maybe you can actually multiply the cells, but you can see that it's very limited. There's not much you can do with this kind of modeling. Okay. Another way to represent the cells in the computer is by using a particle model, where each cell is actually modeled as a point in space with some kind of interaction potential between them. And then these dots here will be the center of each cell. You define some interaction energy. The green here radius is going to be the how much you can compress that cells. The blue radius is the ideal radius of the cell where the energy is minimized. And you can actually have some kind of interaction distance that the cells can sense the next cells up to some kind of gray radius here. And you can use that to actually simulate mini cells to have them interact with each other, okay, come into contact. You cannot change the shape of the cells this way, but there's one way to model the cells by using a particle model. Another way is actually to go into a little more details about the shape of the cells. And what you can do is, instead of modeling the cells directly, you'll be modeling the membrane of the cells, and or the membrane that the cells have with the neighboring cell. This will be the vertex model, where you're actually modeling the vertex of the cells with other cells, and you can specify some adhesion or tension between the membranes that connect those dots, and that to set up the cell properties. So these are the three very basic ways to model the cells on a computer. But another way that to model the cells on a computer is just actually is by convert the image that you have in your computer of the cell into a pixelated image of the cell. So when you see a cell in a computer, in an image, that picture is already pixelated. What you can do is actually convert those pixels into in a grid, okay, and say, okay, this cell here is actually be occupying these grids these pixels in my grid, and I can represent the cell as this collection of pixels. And then this cell on the neighborhood here will be another collection of pixels with some kind of different number, this even a third number, and you can, in this way, you can actually model the exact, not exact, but in a very good approximation, the shape of the cell as you see them in your microscopic images. Okay. What B is again? Yes. Sorry. P here is just a cellular automata way model of the cells, where each cell is represented by a single point in a square grid. Okay, it can be a triangular lattice, a Cartesian lattice, like see here, hexagonal lattice, but each cell is going to be one point in this this grid. So the way that you represent the cells, CompuCell is actually a sophisticated version of cellular automata, if you can say that, because it's actually you can represent the cells with many points in a lattice. CompuCell can do either Cartesian lattice, as you see here, and it can also do hexagonal lattice if you wish to our simulation. We can cover that by the end of the workshop, how you can actually represent your cells with a hexagonal lattice if you want. Okay, so this is how you represent the shape of the cells. Okay, good. But of course, you are doing this workshop because you not want to make a representation of the cells in a computer in a simplified way like this. What you want to do is actually want to move the cells to move, to actually change their shapes, interact with one another. So the way that the cells in this kind of Cartesian grid move is actually by gaining a pixel or losing a pixel at each interaction. Okay, so the way the cells evolve CompuCell is actually by growing a pixel and deleting a pixel at a time. So this is called the pixel copy events. So here is you can actually, let's simulate just that single cell that light up, and what the cell evolve in time is just by copying, changing the pixels from its surface to either growing or shrinking. Okay, does that make sense? So that's how the cells are actually moving in your CompuCell simulation that you just tried in the previous module. If you look at very close, the cells is a collection of pixels in either a two-dimensional or three-dimensional Cartesian grid, and the cell evolve its shape by actually making pixel copies with them around its periphery. Okay, so that's how the simulators are doing. Okay, so cells move via pixel copies. Okay, so how exactly but of course these pixel copies, they have to be guided. Okay, they have to be some kind of logic behind it for your simulation to actually do what you want them to do. So the way that the pixel copies work in CompuCell is actually do one pixel copy at a time. And the way you do that in a random way or stochastic way. So you have your cell here at the left in a current state. And what CompuCell does is random selects some pixel that I will call as pixel I, which is going to be this red pixel. And once you select this pixel, you actually random select a neighboring pixel, which in this case is going to be this one to the right, and you test whatever this red pixel will grow over the green pixel. Notice that there was a cell here, and on the one on the right there was not cell. So the cell wants to grow. Okay, so you have this pixel copy attempt to make the cell grow. Okay, so now how can you choose whatever this pixel grow or not? Is the following. If this drives the cell towards its target properties, okay, so the cell will have some kind of predefined properties that you set up, okay. Let's say the cell wants to be have a certain volume, or the cell want to have a certain surface area, or the cell likes to move to the right, or the cell likes to move to the left, okay. Every time you change a pixel of the cell by growing it or shrinking it, you're either driving the cell state towards this target properties or away from this target properties. Okay. So let's say that your cell wants to grow. It wants to have a bigger volume than it has currently on the left panel. So if this drives the cells toward this target property, so for example, if the cell wants to grow, then you accept this pixel copy, and then you accept it and you move on. If this pixel copy is driving the cell away from target properties, for example, let's say that your cell wants to actually be smaller than it currently is, then this pixel copy make it grow and move away from what you want to do. So what do? You do not accept the pixel copy. You accept it with some kind of probability. Okay, so you may accept or not. If it drives towards its target properties, you always accept the pixel copy. If it drives away, you may accept it with some probability, but it'll be the probabilities be even lower if it drives too far away from its target properties. Okay, this all becomes more clear as we go along. So let's say that the cell wants to grow, so you accept this pixel copy. Okay, so then the new state of the cell now will be the exact one as before, but now with this new protrusion here, because you just accept pixel copy. Now, what does the CompuCell does next? Now it repeats the process again, and it selects a new pixel randomly from your simulation. Let's say that will be select this pixel that is outside of the cell. So the pixel do not necessarily need to be in the cell or outside, can be anywhere in your grid. Okay, and then it selects a neighboring pixel of this one. So here it selects the another pixel which is to be the bottom left of the red pixel, and then it tries to make a copy attempt. So what it's going to be doing here is trying to copy this black space into the cell here. Okay, so you'll be shrinking the cell. And again, the criteria is the same. You look at the way you set up the energies of your simulation, which are the way that what CompuCell will do. It will look, okay, will this pixel copy drive the cell towards its target properties or drive it away from its target properties? So if the cell actually now has a much bigger volume that it wants and wants to shrink, then you accept this pixel copy because you'll be shrinking the cell and the cell wants to shrink. If the cell still wants to grow, then this is a pixel copy that unfavors or drives the cell away from target properties. And in this case, you will only accept this pixel copy with some probability. So you may accept or you may not accept. Okay. So as you do this many times, the cells start to move. And what you see that basically the movie that you have been seeing here. What's going on here, you have many of those pixel copies happening at each step. Some of them are rejected, so you don't see the change in the cell shape, and some of them are accepted, and that's why you see that the cell is moving around during the simulation. Okay, is this making sense? Do you have guys any question?
I have a doubt if I can ask.
Sure.
So how many of those pixel copies actually happens when we press on one step? Let's say if our simulation, if our output increases by one step, how many of those actually happen?
Thank you for the question. That's a great question. So how you define a Monte Carlo step, right? What's a step? What's the unit of time in those simulations? Okay, so let me explain to you. Is the following. So for example, in this simulation, we have, I don't know, 3, 6, 9, 12 pixels on here on the X, and I don't know, I will not count, let's say this is 20 pixels on the vertical, okay? So the total number of pixels is 12 times 20, okay? So 240 pixels. So each unit of time in the cellular plots model or in CompuCell will be 240 of those pixel attempts, okay? So between each one
But the
of the,
pixel chosen is random, you said.
it is random. So some pixel will be
And the same
more than
pixel could be
once,
chosen again.
you can be chosen, and some pixel will never be chosen.
Okay,
Yeah.
I see, got it.
So 240 of those pixel attempts constitute one Monte Carlo step. Okay, that's the unit of time. And you see, if you have a bigger simulation, right, a bigger space, then each Monte Carlo step will be more one of those attempts. But you see that the density of pixel copy attempts per uh, grid lattice remains the same. Does it make sense?
Yes, that makes sense. Thank you so
Okay,
much.
so that is how you define the unit of time in CompuCell, okay, or in the cellular POTS modeling, or the IZ model or POTS modeling, this kind of modes where you're evolving a grid. We do the pixel selection randomly because if you do sequentially, you'll be introducing a bias in your simulation. Okay, you'll be updating this um, surface before this surface, right? And that will be lead to problems. Okay, so we randomly select the pixels, and we randomly select the neighboring pixels, which we're going to try to do the copy attempt. So sometimes we may select a pixel that's right in the middle of the cell to copy to a pixel that's next to it, and that will do nothing, but that's okay. Okay, some of these pixels will be uh, uh, updated. Some of them will not be updated. Okay, I think there's a
Uh,
question in the chat.
no, let answer
Yes,
that first.
Victor. Okay, the question of Ajay. So is a particular fraction of pixels being changed at each Monte Carlo steps rather than a fixed number? Yes, it will be a particular fraction, and it can some Monte Carlo steps may have more pixel change than others. This is very stochastic. Uh, that will really depend on how many cells you have, how is the current state of the cell. So it really varies between Monte Carlo step to the other. Another question, can we do the 204 steps in such a way that each peak select exactly once randomly? I think you can. Uh, you probably give to similar results, but it's not the way we implement it in CompuCell. Okay, I think you give the similar results that what you have before, but what the way we do is by random select the pixels, and some will be selected twice or thrice, and some will not be selected at the given Monte Carlo step. Megan, does it choose a pixel based upon a defined area? No, it's completely agnostic and blind pixel selection. Okay. Of course, only the pixels that are around the cell surface actually be able to do something, right? And I know that some people have been developing algorithms to only select the pixels that actually can do something. But the problem with those attempts is that usually that leads you to more computational is more computation expensive than just select the pixels in a blind way. Okay. So let me see if I no, it just run the pixels around the whole grid. Trying to select all the pixels around the cell requires you to actually know where the cell is, and doing that calculation it can be more costly than just doing it blindly. So doing blindly is actually a more efficient way to do it. Yes, it's also pseudo-random because our random numbers in computer are not really random. They are you're using the random number generator in your from your machine. Okay. Is there any advantage of hex grids over square grids? There might be, depending on your simulation. That's really simulation specific. Yes, Victor. After 200 pixel selections, it will update your Monte Carlo step, and you'll see a new image popping up in your CompuCell player. Okay. Great questions. Is there more? Or do you want me to expand on anyone? Can you control how many pixel flips per Monte Carlo step? I guess that would be the question. Yes, you can, but that's something more advanced. We can teach that at the end of the course, okay? But yeah, there is a way to do it. Great question from Robert Moore. How do you match events with different time scales if the time step is based on pixel selection? There are many ways to do it. So how you define a Monte Carlo step in terms of time, right? So a Monte Carlo step is how many seconds or how many minutes, okay? This really depends on the simulation that you're trying to do. One way to match it is by tracking how the cell moves and match the diffusion time of the cell with the real diffusion time of your experiment or the in vitro or in vivo. And from that, you can adjust the time scales and set, okay, 100 Monte Carlo steps is equal to 1 minute, okay, or 1 second. So this is a good question when you actually go to the hackathon or you actually doing your model, how you match time scales, okay. But there is not predefined way to do it. So it really depends on the simulation that you're trying to do. Of course, the scaling of the pixel size and the micrometers is predefined. Is that's something that is set up as soon as you do your simulation, but the time scales matching that requires a little bit more of work. Okay. Any more questions?
Um, can you hear me?
Yes.
If you if your pixel is selected within the border and it goes out, it copies to an empty space, and
Yes.
the empty space is selected and copy inwards.
Yes.
There will be like a single pixel out and a hole inside.
I don't quite understand. Yeah, so in this case, the cell is growing by 1 pixel, growing 1 pixel into the medium. In the next slide, the cell is actually shrinking by having a medium pixel or empty pixel being copied over the cell. And if that cell is already around its target volume, you have these events going on, and the cell, on average, will not change its volume much, but you'll be changing its shape over time and maybe be moving around the lattice.
Um, I was asking in the sense of let me phrase it. You have a pixel that goes to an empty space, a cell pixel that goes to an empty space, but
Yes.
in the same frame, it selects that empty pixel and copies to the first pixel. You know.
Yeah, that can happen. So,
Uh,
like I said, the next time step, instead of selecting this red one here, you select this one and it copies over this. It can happen, and then you will not see the difference, but you you had two copies of pixels that one kind of erase the other. Yes, that can happen. Was that your question?
Yeah, I think it answers.
Okay. Okay, a question from Derek Stepanova. How is cell integrity maintained? A pixel can invade another cell, which will be a modeling artifact. No, it may be a modeling artifact, it may not be a modeling artifact. It really depends on your simulation. So you may have a simulation of white blood cell chasing bacteria, and when they encounter each other, the white blood cell gonna go over the bacteria and engulf it. Okay, or may have some other cell actually invading another cell, a cell invading another cell, and in this case, you actually want to have those pixel copies of one cell over the other and invading it. Okay, so it may happen. It really depends on your simulation uh, uh, particularities. So it may be an artifact. If you don't want it to happen, it may be actually exactly what you want to model. But that's how cells interact with one another. When they touch each other, you have a lot of pixels copy attempts around the boundary of the two cells that may make a cell actually spread over the next one, or have the other cell spreading over it, or pushing it to the side. Is there a way to control it? Yes, by changing the properties of the cells. Okay, so we'll be going over this. You'll be seeing many ways how you control the cell properties. So today, right now in this module, I'm gonna tell about the adhesion energies. In the next module, I'm gonna talk about the energies that control the cell shapes, and then the module in the end of the day, you're gonna show how you can divide the cell, and then as you go on the course, you'll be covering more things that actually control how the cells interact with one another. Pradev Keshaya, why is only one pixel copy in one instance? If you select many pixels at the same time to do the same thing, you may have a situation where the cell deviates too much from its target volume. Okay, there are ways to parallelize the simulation or this algorithm. You do this by spatial polarization. You divide your simulation to different steps, regions, and you uh, do do the pixel copies on two regions at a time, and then another two regions at a time, and then you merge the results. But that's a conversation for the end of the course. Yeah, there are ways to do it. So there are ways to parallelize your simulation. But when you run simulations today in your computer Nano Hub, they are done in series. Okay. All right. Okay, I will move on in the interest of time, but these were very great questions. Okay, so this go back to one of the questions you just had. How to specify what cells attempt to do? Okay, so all cells and objects in CompuCell have a set of properties and behaviors. So the cell may have a target volume, a target surface area. Sometimes the cells want to actually be elongated. Okay, so have a 2:1 ratio or 3:1 ratio. Okay, a cell may actually really like to be touch another cell or really dislike the interaction of another cell. You can have the cells move in a certain direction or move away from the gradient, and all these kind of different behaviors that the cell may have will influence which of those pixel copies will be accepted or rejected. Okay, and they are all set up in the form of energy terms. Okay, so each cell or the simulation itself has some kind of master energy. Okay, or a Hamiltonian if you have a physics background, and you can have different terms in this energy cost function. Which one of those energy terms you're going to specify the volume of the cells, the surface preference of the cell, the length preference of the cell, the contact preference of the cell, and so on. And we'll go into each one of these energy terms in more detail later. Okay, so a simulation may have only volume constraint. Some simulation may have only contact energies. Some simulation may have all of them together. It's up to you to choose which kind of uh, behaviors you want to actually enforce your cells to have. And some cells may have a volume constraint and a surface constraint, and some cells may have just a volume constraint and a aspect ratio constraint, for example. Okay, uh, you can model different cells with having different properties. Okay, so there's a lot of flexibility in the way you model the cells. Okay, and that again will depend on exactly what exactly you want to model. Okay. Uh, so when do you accept or reject a pixel copy attempt? Okay. So the way that it works is the following: you have a current state of your system, like you have here on the left, and you calculate all the energy of the pixels, and you have an initial energy hi, and then you try to do a pixel copy event like this one here on the right. Okay. If you accept this pixel copy attempt, you'll be changing the energy of your system or the energy of your cell. So you have a new final energy, HF, H final. Okay. So between this and this, you have a change in the total energy of your system, delta H. Okay. So when do you accept the pixel copy? When you reject the pixel copy? Well, if this change in energy is actually decrease, if this pixel flips actually decrease in the energy of your system, you always accept the pixel copy attempt. So if your change in energy is decreased energy, so it's negative, you always accept the pixel copy. If this actually is increasing the energy of your cell, of your system, then you may or may not accept pixel copy depending on the probability. So in this simulation, in CompuCell simulations, we accept that using a Boltzmann distribution. Okay, you accept this probability by the exponent of minus the change in energy divided by some gouging parameter called t. Okay, so this t here actually will define the shape of this curve here, and you can if you have a physics background, this is going to be the temperature of your Eisen system or pot system. But in the case of CompuCell simulations, this can be interpreted as the noise level of your system or the level of membrane fluctuation of your systems. The bigger this value here, the more pixel flipping events that drive up the energy you accept. So the cell can change more, has more freedom to change its shape before minimizing its energies. But if you make that parameter t to be lower, you'll be effectively only accepting pixel copies that minimize energy. One question is, okay, why do you want to have this kind of parameter? Why do not only accept the pixel copies that decrease the energy of the cell? The problem with only accepting pixel copies that decrease the energy of the cell is that very quickly your cell will reach all its ideal shapes, ideal volume, ideal surface area, and ideal volume. Okay, and once the cell does that, any other pixel copy that you try will be rejected, and then the cell will freeze in your simulation. Okay, so if you just accept the pixel copies that minimize the energy, after 3 or 5 Monte Carlo steps, your system is dead. The cells change their shape and they freeze in their current shape. So actually, you want to do a simulation where you actually accept some pixels copy attempts that drive the energy of your system higher, because that actually allows the cells to actually move and not die in the simulation. So you want to allow the cells to actually fluctuate around its target properties, so that actually the simulation will actually be so this actually can do something, right? If you only minimize the energy, you'll be freezing the system very quickly. Okay, remember the cells live in a stochastic and non-zero temperature environment, so the cells do many things that may be energetic unfavorable. Okay, you may think of this way. They are in a thermal bath. They are not at 0 Kelvin temperature.
Julio,
Yes.
so okay, the Boltzmann, let's say, the Boltzmann distribution allows the cell to fluctuate around a certain equilibrium.
Yes.
But Robert asked in the chat, what if we wanted to use another function for probability acceptance if we don't want to use the Boltzmann distribution?
Okay, I think you can. Well, okay, I do not know if CompuCell allows you to change that. You can certainly, well, CompuCell3D is an open source simulation, so in principle you can change the C++ code that's underneath to have another probability, a different way, a different acceptance function. But well, if you, I assume that you may have a very good reason to do this. There is a way to do it. You can change the code. At the very last day of the course, we may be teaching how you can build your own functions at the C++ level, and this will be one thing that you probably can do. But of course, it's a very advanced way to work with CompuCell. Yeah, so James already answered this in the chat. Yes, you can do that in principle. Okay. Okay. Okay, so let's go on. Very good question, by the way. So, how are the cell properties and behaviors written in terms of energy? Okay, so usually we'll be doing some kind of Hooke's law type of energy terms. Okay, so we have the initial energy HI, HF, and the cell may accept or reject this pixel flip whenever you are minimize the total energy of the system. And your cell may have a volume constraint, a surface constraint, a length constraint. Okay, so usually what you want to do, you want to have the cell have some kind of target ideal volume that you want to have, an ideal surface that you want to have, an ideal length that you want to have, and you model each one of those constraints as basically as a spring. And this here for the volume, for example, V is the current volume of the cell in number of pixels. This V target is the ideal volume that your cells want to have. And what you do, every time you have a pixel copy attempt, you recalculate the energy, and you see that any deviation from the current volume to this target volume is squared. Okay, and there is a term here which is called the strength of your constraint that sets up okay how much you tolerate deviations of this target volume. Okay, so basically the cells have a target volume. Let's say this may be, let's say 100 pixels. Okay, and if it's and your cell may be sitting right here, maybe have 99 pixels, and you have a spin flip that drives the cell, a pixel copy attempt that drives the cell towards its target volume, that will be decreasing the total energy of your cell, and you accept the spin flip. If it's driving further away from its target volume, that will be increase the energy of your cell, and then you accept some probability. Of course, the cell may have a volume constraint and also a surface constraint or a length constraint. In this case, you have all these terms being affected by each spin flip, and the way you decide whether you're gonna accept the spin flip or not, you have to sum how all of those terms change the energy and see whatever the total energy of your system is going up or down with the spin flip, and then you make a pixel copy attempt based on the global minimization of your cell target properties or target properties. Okay, so this makes sense. So usually all the target properties and behaviors of the cell are specified by this kind of hook law or spring-like uh, um, energy term, where you actually calculate the deviation of the cell current property from its target property and see wherever you're driving it away towards or away from it. So this would be target. If you have a volume that's higher than target volume, that's penalized. If you have a volume that's lower than target volume, that's also penalized. So that's why you have this kind of square here in your energy terms. How are ideal lambda parameter values chosen? Okay, that's a good question. That depends. It's a little bit of an art, okay? But remember that your energy term is, you actually are choosing that based on the, with respect to your noise level of the system. So usually you want to choose a value of those lambdas that are about the same value as your T, as a temperature or membrane fluctuation level, okay? But there are many things that affect that, okay? So you cannot have a temperature of 1,000 and a lambda volume of 1, okay? That would be too weak. And at the same time, you don't want to have a temperature of 1 and a lambda volume of 1,000, because that is too strong, okay? So the lambda is similar to a tuning parameter, so you have to, actually that's the next slide, okay? You have to basically do a little bit of trial and error, and the judgment will be, look at your simulation and tell me, do the cells look like they're behaving properly or not, okay? So the next exercise here will be to try is a way to drive your intuition about how exactly choose those parameters. Does the cell look realistic or they do not look realistic? If you are way off, the cells either will look not move at all, or they'll be fragmenting. Darshan Shah, if for interaction, the global minima is the local minima at, you always driving their system to preferentially towards the local minima, okay? The global minima of a simulation will be will be a simulation with no cells, okay? Yeah, for one interaction or energy, yeah, as Pedro said, should decrease a little bit. It may go up a little bit, but you don't want those fluctuations to be too high, otherwise the cell will not look right. Okay. Good question, Ajay. Yes, in a two-dimensional simulations, when you say volume, this is actually this area here, the number of pixels that you see here. In 3D, the volume constraint is actually the volume is the number of pixels or voxels that represents the cell. Okay, so we did stick with the volume name for this energy term, okay, because, well, when you do a two-dimensional simulation, you are basically assuming that the cell extends in the z direction, okay. But yeah, in 2D, the volume means the number of pixels, and in 3D, the volume means the number of voxels in your grid. And the surface will be, in this case, in 2D, the surface will be the number of sides, okay, of the pixels. And in 3D, it will be the number of faces of your voxel. Does that make sense?
What does length correspond to when you go to 2D?
2D will be the major length of your cell, okay? So it'll be the distance. So in this case, you can see that the cell is elongated. So it'll be the distance from here to here, approximately. It actually calculates the moments of inertia of your cell and takes the major axis and see if this major axis length is equal to this target length. But it will basically be the major length of your cell. Does it make sense? Any more questions? Okay, so with this very basic introduction, I want now to ask you guys a question, okay? And the question will be, I want you guys all look at those two simulations, okay? So it's two simulations of a cell moving, okay? And I want you to look at them, compare them, and tell me which one you think is correct, looks more correct, and which one you think is looks not quite right, okay? So I'll play this one and this one, okay? And I want to write in the chat, okay, which simulation is more believable, okay? Which ones looks right, which ones looks wrong. Okay, so most of you said that the right one looks wrong and the left one looks better. Why? It's basically the cell integrity. The cell on the left looks is a single cell, right? The cell on the right sometimes divided into 3 or 4 and it's very fragmented. And it does just not seem. It's the same simulation, right? What did it change here? We changed the parameters, okay? They have the same energy in terms of the coding. If you look both codes, they actually are the same structure. They both, the cells have volume, the cells have surface constraint, the cells have directed movement towards the top right. But in one of them, the cell looks, you all said that the cell on the simulation left look better and the cell on the right looks wrong, okay? What changes the way you choose the parameters, okay? So let me show another one now. This is a single cell. Now let's look at a simulation with many cells, okay? It's a self-sorting simulation. And again, I want you to tell me which one looks better, which one looks wrong, worse. Okay, 4 votes for one of them. Yeah, it's true, Sahana. Overall, they look the same. You get the same endpoint, right? You do have sorting of the blue cells toward the middle, and the green cells go to the outside. Okay, but most of you said that the left one is better. Why is the left one better? Well, again, maybe I can answer. Maybe the left one looks bad because you can clearly tell the outline of the blue cells, while in the right you cannot tell the outline of the blue cells. It looks like a meshed. But very good, Sharon. I was going to say that right now. The green cells on the right are tend to be orthogonal. They are kind of lining up with the lattice. Okay, that is an effect called pinning. So that does not look realistic. Okay, the cells are not really square. Okay, so when you see the cells that are look like in the blue cells here on the right, you can really tell that okay, that does not look right. The cells are not like that in real life. Okay, But I have seen some publications where the cells actually look like the green cells here on the right. They are very squarish, okay? And that's something that actually you made a similar mistake but in the opposite direction, okay? The cell is too stiff, okay? The You set up your maybe a volume parameters or target surface parameters too strong, and the cells tend to align with the grid, and that also does not look right. Okay. All right. So this is what you probably want to be learning. Okay, how you make simulation, make sure that you choose the right parameters so the cells look realistic. You want your simulation to always be look more like the examples on the left than the examples on the right. Okay, and this you have to do with some exercise. So let's proceed to exercise because our time is short. Okay, so what I want you to do today is actually play with one of those addition energy terms, which will be the contact energy of the cells. And we can use that actually to model epithelial to mesenchymal transition of the cells in a very simplified way. So very shortly, epithelial cells are cells that are very squarish, they're very compact, they actually adhere to the neighboring cells in a very strong way, and they form sheets, right? And compact tissues, while the mesenchymal cells are cells that actually are able to move. They do not adhere to one another. They can crawl and move into around the tissue. Okay, so there are a lot of epithelial mesenchymal transitions. The cells can, from epithelial state, can become mesenchymal and vice versa. Okay, and during development, the cells actually undergo many of those transitions. You can have a primitive epithelia that becomes mesenchymal and then creates a second epithelia somewhere else in your cell, or you can just have epithelia that transforms to fibroblasts, which is another type of mesenchymal cell, and you can have epithelial mesenchymal transition, something that actually happens during cancer development. Okay, so those are cells in your cancer, they can start divide, and then at some time they may undergo the epithelial to mesenchymal transition, and that's very dangerous because that's when your cancer cells can actually spread throughout your body and then start making tumors on other places. Okay, so what I want to do now is for us to undergo some exercise of how to model how the cells stick to one another or do not stick to one another, and that's done with the contact energy plugin of CompuCell3D. So I want you all to open up a new simulation on NanoHub or in your desktop. Okay, so please log into NanoHub, open the open Tweedit, and let's do the following. Let's go to CompuCell3D project on the menu, new CompuCell3D project, click there. Okay, please do this, and let's make a new simulation call. Let's give a name, module 121 underscore EMT. Okay, sorry, that's little space that I have there, it should not be there. Okay, when you give a simulation name, no space, no dots, and no slash in the names, and the name should not start with a number. Okay, so just create a simulation call. It can be whatever you want. I suggest module 121 EMT, and select Python plus XML. Okay, once you hit that, hit continue. Okay, this will give you another little window, so you are actually working in the simulation wizard, and here you can actually specify the size of your grid, 256 on the X, 256 on the Y, and 1 on the Z, so it's a two-dimensional simulation. You don't have to do anything on that thing, just leave as it is, and hit continue. Victor Lorenzo got an error. What error did you got? Okay, can someone please help Victor with his error? Okay. So I probably have to save your simulation in another directory. Okay. So if you, I have to go quite quick here because we're running out of time, but please enter the breakout room and either Pedro or Hayden can help you if you have issues. Okay. So next you hit continue here. So in this window, leave everything as it is, hit continue, and then you have a new window called cell type specification. So here you actually have to tell CompuCell which cells you want to model. Okay, so what you have to do here is initially all the simulations have the medium by default, and I want you to add a new cell type, and it can be whatever name you want. I'll just call it my cell. Okay, we have to type my cell here, and then you have to hit add. So once you hit add, then you populate this thing here. So now we have medium and my cell, and once you add the cell there, then you can hit continue. Okay, so make sure that you write a cell type name. It can be mesoderm, it can be epithelium, for example. It will also be a good name. I'll be using my cell because I lack creativity. Okay, so make sure that you type here, hit add, make sure that your cell appears here, and hit continue next. Okay. Okay. Once you hit continue, you have another window. If you want to add chemical fields, we do not want chemical fields, you just hit continue. And then this is very important, is it asks you what kind of cell properties you want to have in your simulation. So here make sure that you have contact and volume flex selected. Okay, you want your cells to have a volume, and you want your cells to have contact energies with their neighbors. Okay, so select contact and volume flex, ignore the rest, and hit continue. Once you do that, your simulation is done, and the CompuCell3D just created your simulation template for you. Okay, so hit done, and then what you see once this is done is that you have your 3D, and there's a small entry called with the name of simulation. Okay, you can just go ahead and either click on the CompuCell3D logo there, select this, click on CompuCell3D logo, or right click on the name of simulation and hit opening player. Okay, so please do this and tell me what do you see in your simulation. Did everyone got a simulation running or not? Maybe I should go back to the list of you just got a blue box simulation. Yes, a square.
Yeah, so it's just a blue box, and then it's changing the pixel around.
Yes, I see square block of cells. Okay, so if everything worked out, what should be seen is something that looks like this. Okay, a square bunch of cells. Okay, which over time kind of rounds up. Okay, so remember, once you got in simulation, you can control the simulation by hitting play, this step simulation, one Monte Carlo step at a time, this pause the simulation, and the last button here, stop simulation. And then once you hit this, it's over. You have to hit play again to run. But you should be seeing something that looks like this. Okay. a lattice with a lot of cells. Okay. Okay, got it. So that's, if you see a square block of cells, that's where you want to be. Okay. And of course, my cells are orange. Your cells are likely blue. Am I correct? And if you don't like your cells to be blue, you want to be another color, there's a way to change the color of the cells. Okay, this is outdated. One way to do it is actually click on this tools button here, and this allows, open up some window that allows to change many properties. But in the new version of CompuCell, you actually can directly click on the red there and change the color of the cell. Okay, so you want your cells to be pink, you can do that. Okay, so what's going on here? Okay, so two things are happening in simulation. One is a short term and one's a long term. So you see that the way you initialize your cells is in a square, and all the cells are square. Okay. Okay, so that's how it looks like. So the first thing that it is going on is that the cells are adjusting, making spin flips and adjusting their shape. So in the very short term, what the cells do is they minimize the surface energy. So now they went from a square configuration to a more rounded configuration. So the cell relax their boundaries. Okay. In the long term, the whole tissue, which starts as square, is also relaxing its external boundary and start to round up. Okay. So if you run a simulation for a very long time, if you just keep letting it run, eventually you get the tissue to now start to look more like a sphere or a circle because it's 2D. Okay. I didn't change any property. Okay, I just let that simulation to make simulation with one cell, and this is just what's going on. Okay. So are you get your cells to first round up and then the tissue to round up? Okay, I hope you're getting this. Okay.
Sorry, I was in
Yes.
the breakout.
Yes.
You change any property, or
I
you
didn't
just
change any property. I just moved on with
next?
the
Right.
with hit next, and with the standard values that CompuCell gives you, this is what happens. Okay.
Cell medium type.
Yeah. Let me go back here a few slides. Yeah. What we did, we just add a cell in the simulation, right? And then did do no chemicals, and then I will select contact, volume flex, and that's it. Just play simulation, and you should get something that looks like this. Okay. Got it?
Contact, volume flex, center of mass. Just
Yes.
these three?
Just these
Correct.
three. You actually don't need the center of mass, but you can leave it there. Okay, so what's going on in simulation in terms of energies? Okay, so you only have the volume, which is, we already saw how it works. That just makes sure that the cells do not disappear and all they have the same volume. But another thing that's going on is the cells are having interaction with the neighboring cells to the contact energy term. Okay, so this contact plugin is one of the most used in CompuCell3D simulations, and it's quite different from the other ones. What goes on is that you have a matrix of interaction between cells of a given type with cells of different types. Okay, and that specifies the energy contact energy of one cell type with another cell type, or of cells of the same type. So here this matrix, which called just this J matrix, specifies the energy between cells of the type A and type A, cells of type A and type B, cells of type A and type C, and so on. And of course, uh, energy between the energy of cell of type A and type B is the same thing as the energy of type B with cell of type A. Okay, so every time a cell changes surface area, this contact energy of the cells is recalculated based on the how you change the surface of the cell with respect to the neighborhood. So the way it works is the following. You calculate this contact energy by picking up a central pixel, which usually will be a pixel at the boundary of the cell, okay? And then you look at its neighborhood, okay? And you say how many neighbors this pixel has, okay? In this case, you're looking over this uh, whole neighborhood here inside the green, and you're looking over the table and calculating the, okay, this have an energy between the gray cell and this gray cell, this gray cell and this gray cell, oh sorry, this gray pixel and this gray pixel, this gray pixel and this gray pixel, this and this gray pixel and this white pixel, this gray pixel and this white pixel, and so on. So you do this for all the pairs between the central cell here, the central pixel here, and the pixels around it. And you do this for this pixel, and then you do it again for the next one, and the next one, and the next one, okay? And then you sum all of this, and you see how much your energy changed, okay? So in our simulations, we only have two cell types, okay? The first cell type is the medium, okay, with the black space around the cells, and the other cell type is the micelles, okay? So our matrix of contact interactions only have three values, okay? The interaction between medium and medium pixels, my cells, your cells and medium pixels, and cells and cell pixels, okay? This energy only applies to cells or objects that are of different type. The cell does not, a cell pixel does not interact with a pixel inside the cell, and the medium pixel does not interact with another medium pixel because you only have one medium. So effectively, you only have two contact energies in this simulation: the energy between cells and medium, and the contact energy between cells of different cells. Okay. Okay. So you actually only have these two values here on the right in bold. Okay. So actually, this simulation only have two numbers that you actually have to care about: the contact energy between cells and medium, and the contact energy between the cells. Okay, neighboring cells in this case. Okay, so again, I'm not showing this one here because it's redundant. Okay. So now so how exactly this affects your simulation? So we can actually start by increase the contact energy between the medium and the cells, which is currently 10, and let's make it higher, 20, okay? So all the CompuCell3D parameters can be changed either in the player or the XML code, okay? So in the tweedit, if you go back there, you can double click on the name of your simulation, okay, and that will open up all the files associated with your simulation. Don't worry about the Python files. What you have to do, you have to click on the XML file, and once you click there, you'll be opening up XML with a set of instructions of which kind of energies your cell wants to have, your simulation has, what's the size of your lattice, where you draw the cells, what will be initial condition, how many steps you want your simulation to have, and so on. Okay, so I want you all to go to tweedit, double click on the name of your simulation, and then click on the XML file, okay, and open it. Elena, yes, there is. Okay, the short answer, yes, there is. That's how one of the ways you calculate or the main way by which you calculate surface tension in your cells. Okay, if everyone's here now, I want you to go to the place of your code where you actually specify the contact energy. And that should be around line 36 in your XML code. And you see that you have there a plugin named contact and say specification of additional energies. And then you have all the three combinations you may have, medium and medium, which actually is a known combination, medium and micelle, and micelle and micelle, and they're all set up to 10, okay? You also have this other thing called neighborhood order that basically tells how far away you look from one pixel to neighbor pixels. Hi Megan, exactly by this thing here, the neighboring order. Okay, we go into more detail that in a few slides. Okay, neighboring order 1, it's going to be just the pixels right above and right left. Neighboring order 4, you see that bigger radius. Okay. Okay, so the first one here, you don't care. You want to increase the addition between the medium and micelles from 10 to 20. So let's change that to 20. Okay, once you change that, save your simulation, and then you can hit play again in the simulation. Okay, so please make this from 10 to 20 and save. There are two ways to save simulation. You can either click on the save icon. For those of you that are much younger than me, this was supposed to be a floppy disk. Okay, so that's what this thing is, thing that you put on your desktop to actually save files and transport them. So this is the save button, but you can also click just file, save, and that will save your simulation. And you know that your simulation is saved because once you make and edit your file, it becomes red. If you save it, it becomes blue again. Okay, so make sure that your files are blue. You save them before you play them in the player again. Before you play in the CompuCell player. Okay. Okay. You can also use the shortcut Control S or Command S if you are on the Mac. Okay, so you do this, you play, and tell me what you see. What happened when you increase the energy between the cells and the medium? Okay. Can anyone tell me what happened? Cells minimize their contact with the medium, round up much faster, became round faster. Okay, why did that happen? Okay, round their corners, excellent. Okay, so okay, yeah, so let me just skip this. Okay, so yeah, this is what you more or less will be seeing. Okay, so when you increase the energy between two cell types, or between the cells on the medium in this case, actually you do not like that interface anymore. Okay, so in higher energy, and remember you are minimizing the energy of your system. So the way that you minimize the contact, so a higher energy between the cells and the medium means that you want to minimize the contact surface between the cells and the medium. So when you do this, what happens is that it runs up faster, and you actually, the surface between the cells and the medium becomes smoother. Okay, if on the reverse effect, then what you have to do, you have to actually decrease the energy from 10 to a lower value. Okay, but notice that this there is a very big difference between what your original simulation looked like and what your simulation now looks like. But the interface between the cells themselves is not affected. If you outside, it's round up faster, but inside the if I just make a zoom up of these cells here and these cells here, you cannot really tell the difference, because what's happened in the bulk of the tissue is just regulated by the energy between the cells and cells. and that has not been affected. Okay, so if you now decrease the energy between medium and cells to 5, what do you expect to happen? Okay, and what does it actually happens? Okay, actually I'll do this, go this a little bit quickly. Okay, you can just try doing your simulations. So if you decrease the energy between medium cells, right? Now the cells like to touch the medium, okay? Because that has a lower value. Actually, they prefer to touch the medium than to touch other cells, okay? To be in contact with other cells. And that leads to a rougher surface of the cells with the outside medium. So you'll be seeing something that looks as in the picture that I have here. Is that what you get? Yes, Norma, yes, Ivan, okay. And does it make sense why this happens? Okay. Okay, everybody's saying yes, I will proceed. Okay. So in the two simulations, we change the way that the cells interact with the medium, but you're not changing the way that the cells interact with themselves. So if you just zoom in inside the bulk of the tissue, the cells look exactly the same as one another, is because you just change parameters that affect the outside, not the internal cells. Okay. So we can actually now go and start to change the parameters that change the internal cells. Okay. So, okay. If you decrease even further the contact between cells and medium, you actually can have this thing happening. Okay. This is important. Try to do this. I should not have shown the image before, but if you make it even lower, yes.
Julio, I have a question.
Yes.
So what's stopping the cell when you have contact energy equals to 5 between medium and cells, and contact energy is 10 for cell? The side cells, why can't they just go to the media? They're not fully going to the media. I see some flips wherein the cells actually detach and then come back to the same place, like the cluster. Why is that happening? Although the contact energy between the cluster and the cell is actually higher than staying there.
Well, there is difference between those energy between the cell has a lower energy with the medium, but the difference is not that great to make the cells completely detach, right? The cells still like one another, so you have to drive the difference in energy a little bit further, like we did here, and then you actually drive the fragmentation of the tissue in a more consistent way. Okay.
So do you think if we run the simulation where the contact energy is 5 and not lower than that for a longer time, you will see that sort of fragmentation to happen? Like, will it happen over a larger period of time?
I think
because
so.
Because it's just that the probability is not high enough for it to detach, and it's I believe that's what's happening. It's probably lower than the Boltzmann distribution. That's why it's not proceeding.
Mm-hmm. Yes, it'll be more. If you just make a small difference, it may be not enough to actually drive the fragmentation. The bigger you make the difference, the more likely the effect will be. Okay. And you can see that the fragmentation happens in layers, as Pedro said. The outer ones have to spread, so the inner ones can then start spreading as well. Okay. Actually, if you change the temperature of a system, you can also make this faster or slower. Okay. If you make temperature too high, you'll not be driving much thing. If you make the temperature lower, even if a small difference, you may have fragmentation for the tissue. Okay. But the problem is that once the cells reach their target volume, they don't want to change their value anymore, so that maybe actually backfire on your simulation. So if you make, so going back here to the this slide, if you make the contact energy even lower between medium and cells, now the cells really like to be in touch with the medium, and they start fragment. So what you have here is on the left a simulation where the cells are compact and adhere to one another, and as time goes on, they fragment and spread, so that will be similar to mesenchymal, epithelial to mesenchymal transition. And we did this just by making the cells prefer the medium more than they prefer themselves. Okay? Did all of you got something that looks like this? Yep. Okay, good. Okay, so let's proceed. Okay, so another thing that we can do, we can now change the energy between the cells. Okay, so let's set back the energy between the cells and the medium to 10, which was the value we had before. And now let's decrease the energy between the cells themselves from 10 to 1 and run simulation. So write in the chat what to expect to happen and why does it happen. Okay, so I already give the answer, but hopefully you get the same thing in your computer, in your simulation. If you decrease the energy between the cells from 10 to 1, what will happen is now the cells really like to stick to one another. Okay, so actually they have to want to maximize the surface area that they have with other cells. So when you do this, what happens is that the cells now, instead of being round as before, they want to actually almost fragment. Okay, they would like to actually change their shape and become more elongated, more rough, so they will maximize the surface of their surface with the surface of the other cells. Okay, yeah, the cells want to be close, not only closer together, they want to be actually have share, they want to hug each other, because they want to maximize the surface, the contact area. And you may notice that because the cells do this, this helps the rounding up of the tissue in a different way. The cells not only change their shape to become very irregular, okay, but the tissue outside also rounds up a little bit faster because the cells inside are more fluid-like. And because the cells are more fluid-like, that facilitates the rounding up of the tissue that before it took much longer to happen. So you're not only change the way the cells interact with one another, you also change the fluidity of the tissue within. Okay. So this is like having the cells to be.
If we put a surface area constraint on this, then this will not happen, right?
Then well, it depends on how you drive the surface area. If you make the surface area to have a target surface that's much bigger than the cell would expect to be if it has round up, then you actually drive it to even more
stretch.
Stretch. If you make the target surface to be smaller, okay, that will be the next module. Then this will kind of go against this and make the cells still be more round, even though they want to do this. Very good question. Yes. Darshan, can we dynamically change these values during the simulation via some functions and methods? Yes, you can. You do that from the Python level, and that we'll be going over this in the next days. Okay. Any more questions about this? If not, let's go on. And So there are basically two ways to promote the. So what we did in the previous simulation, we promote the fragmentation of the tissue, right? By changing the energy between the cells and the medium. And in this example here, we are promoting cohesion of the tissue by changing the energy between the cells and the cells. Okay. So what will happen if you make the median cell equals to 1 and the cell and cells energy equal to 1? Okay. So, for example, if you make median cell equals to 1, you are driving the fragmentation of the cells, the tissue. And if you make the cells and cells energy to 1, you're making the cohesion of the tissue. So if you make both equals to 1, would anything change? Or with one win over the other, what do you expect will happen? Please try to do the exercise. But while you're doing the exercise, you can also tell me, you can either do it directly and see what happens, or you can also change the, just think about yourselves and try to write what would be your hypothesis on the chat, in the chat.
Hey, Julio.
Yes.
I just want to let you know, we decided, since we're already running over into the extra session, we're going to move that to tomorrow and combine it with session 1 tomorrow morning. So you have until 2 o'clock now before we break for lunch, just to let you know.
All right. Thanks.
We got about 20 more minutes.
All right. Okay. Did anyone run simulation? Could and tell me what happened? Okay, I'll just show here the result. Well, this is what I got, and maybe you also got something that looks similar. Okay. So what happens is that, well, when you change the addition energy between the cells to be much lower, you do lead to the change the shape of the cells between the cells. They are very regular. They want to kind of maximize the surface area between them. And but because the cells are already have a rough area, it's very easy to then to maximize the surface of the cells themselves and the medium. So the tissue still become one tissue, right? It did not spread, but the outer surface area of the tissue with the medium becomes very rough. It's not smooth as before. Okay. And the reason that the cell did not fragment as we had before is because even though the cells want to maximize their surface with the medium, they also want to maximize the surface between themselves. Okay, and so the second, the low addition energy between the cells prevents the fragmentation of the tissue. Okay. This mouse square here within the cells is fragments of a neighboring cell. Okay, so it's the fact that some people have asked it before. By the nature of the spin flips, because it's stochastic, you may have, and the cells want to maximize their energy with the neighboring cell. You might have situation where a little piece of one cell ends up completely inside the other cell. Okay. So it's just little, I cannot tell whether this belongs to this cell or this cell, but is a piece of another cell that happens to be inside that cell. It will disappear in the next spin flip, Monte Carlo step, but it happens throughout the simulation. Okay. So probably this is an indication that we drove the energy too far. It's too low. Maybe using addition of 2 will be a little bit more realistic. you prevent this from happening. Okay. So some of you may or may not have this question. Okay, we set up those two energies to be equal to one another, which will be on, but at the very beginning of the exercise, we had also those two energies equal to one another to be 10. Okay, so the question is why this simulation looks like this and the beginning simulation looks like completely different if the energies between the cells and the cells in the medium are exactly the same. Okay, does anyone has an idea of why they look different? Okay, Daria already gave the answer. Okay, yes, it's the temperature. Okay, or the noise level of your simulation. Okay, even though they have the same parameters, they're the relative to the noise level simulation, this one is the left one is much more noisier than this right one. Okay, it's because the temperature is the same between those two. Okay, so what happens that before if you make the energy of those two cells, before you have this energy to be equal 10, so you are more about like here, if you decrease the energy, right, it's much more likely to accept spin flips, so that's why the tissue look like that. But one thing that you can do, we can actually, if you decrease now the temperature by a factor of 10, right, now this energy that you had here before will be equivalent to the same energy as you had here before for the equals to 1. Okay, so when if you change now, adjust the temperature, you can actually make the left one to look like the right, or the right one to look like in the left. Okay, so all those values that you choose for your constraints are relative to the temperature or the noise level of simulation. All simulations in CompuCell, when you start, have a default temperature of 10, and you can choose all your parameters with respect to this temperature, or you can also, if you have too many energy terms and you want yourself to look a little bit more loose, instead of changing each one of those terms values, you can just change the global noise level or the temperature, and that will affect all the energy terms equally, okay, by the same amount. Okay, so if you repeat this, okay, then you should get exactly the same results as you had before. Okay, so if this energy is and this energy is 1 and the temperature is 1, that's equivalent to have these two energies equals 10 and the temperature equals to 10. Okay, does this make sense? So let me go now to the final exercise here. What we did on exercise 1.23, we set our parameters to medium cell 3 and cell to 10 and temperature 10, and choose fragmenting into pieces like this. Okay, and this happened because the cells like to be in contact with the medium more than they like to be in contact with themselves. Okay, is there another way that you can fragment the tissue? Okay, actually there is. Okay, another way to fragment the tissue is to make the is by changing the energy between the cells themselves and make them not like to stick to one another. Okay, so another thing you can do, you can make the energy between the cells to be much higher than before. So you can make the energy between cells to be 30 instead of 10. Okay, so this, what does that mean? This means that the cells prefer to touch the medium than to touch themselves because they have a much higher energy than before. okay? And in both cases, you are favoring one type of contact with respect to the other type of contact, okay? So in those both cases, you should fragment the tissue, okay? But would the tissue fragment in the same ways if you choose one method versus the other method? So I ask you this question and ask you to try this and tell me if the result is exactly the same or there's a little difference. Okay, seems to be the same process, but slower. Okay, that's interesting. Victor said it's different. How different it is? In the first cell seems invasive to the medium, while the second cells are just avoiding each other. Rosie, for two the cells are rounder. Yeah. Victor said that in one of them the cells immediately start to spread. Okay. Yeah, there might be difference in time scales, but besides the different time scale, there's also difference in the cell shapes. You're telling me. Okay. Okay, so should be more or less what the cells, the simulations look like. Okay. Okay, so in one of them, the cells, when you decrease the contact between medium and the cells to one, the cells look very loose and they look like this, as here on the left. While in the second method, where you just increase the energy between the cells, what they want to do is just want to avoid one another, but they do not necessarily want to maximize their contact surface with the medium, right? So they just separate, but they remain their shape remains the same. Okay. So in both cases, you are leading to fragmentation of the tissue, but the two ways that you actually achieve that is very different. Okay, the reason that they're fragmenting is different. On the left is because the cells want to go to the medium. On the right is because they don't like each other. Okay, and they do not necessarily like the medium as well. So they fragment, but they maintain their shape. While on the left, they fragment and they actually change their shape to be more kind of irregular. Okay, so tell me, if you want to model mesenchymal epithelial to mesenchymal transition, right? Which method you choose? The one on the left or the one on the right? And why? Well, you just have one vote for the left. Wouldn't depend your system. Yes. Well, it depends on your simulation, but yes, everything will be dependent exactly on your system that you are modeling, right? But I'll say that if you want to change epithelial to mesenchymal transition, right? Your cells in the end of simulation they should look like mesenchymal, and a mesenchymal cell is much more similar to the situation on the left than the situation on the right. Okay, the cell should be spread, have a regular shape. That's what one of the characteristics of a mesenchymal cell. So I'll say that the left maybe look a little bit more realistic if your cells in the end of the fragmentation process should be epithelial. Okay, if by the end of fragmentation process your cells should still look like round, they're not necessarily mesenchymal, then the right one will be the right way to choose. So you see that we play with just one contact, one energy term in your CompuCell simulations, the contact energy. And even though it's a very simple system, right, you basically have just two parameters plus a temperature, you can modify it. The effects that you have on your simulation are very rich. You can do many different things. You can even have the same final outcome by two different methods, okay? And I want you always to look at how the cells look like, what did the shape look like, and does this shape look realistic? Does it match what I'm trying to produce? Okay, and if it does not match, how can I tune the parameters for the cell to look exactly what I want? Maybe you want to model epithelial to mesenchymal transition, but your simulation looks like the one on the right. And then, oh, the cells are round, they should not be round when it becomes mesenchymal. So now, hopefully with this exercise, you have a better idea or intuition or where you have to change in your code, how you can tune your parameters to actually get the cell to have the shapes that you want them to have. Okay? So with this, that's the end of this module. I hope it was helpful to you. Please do take the time to take the survey.